Physics operates on a grand ambition to find a single mathematical framework that describes every underlying rule of the universe. This master equation is most necessary at the extremes, moments where reality is pushed to its absolute limits, like the chaotic heart of a black hole or the explosive first fractions of a second of the universe. Despite its name, a theory of everything does not attempt to explain complex emergent systems like weather patterns and cellular biology or global economics. Its purpose is strictly foundational. It has to perfectly unite the four fundamental forces of nature: gravity, electromagnetism, and the strong and weak nuclear interactions. Yet, after more than a century of intense effort, no such unified theory exists. We are left with a glaring hole in our basic understanding of how reality operates. The problem stems from how we currently describe the universe. On one side, we have general relativity. It maps the macro world, defining gravity as the smooth, continuous, and highly predictable curving of spacetime. On the other side is quantum mechanics. This governs the subatomic realm, which operates on probability. Down there, everything is jittery, uncertain, and defined by chance. As long as these two pillars of physics stay in their respective lanes, the incredibly massive and the incredibly microscopic, they work with flawless precision. The crisis occurs when a physical scenario demands both. If you try to calculate the physics inside a highly compressed, ultra-dense singularity, their mathematical languages violently contradict one another. This brings us to a technical failure known as non-renormalizability. When physicists attempt to apply the jittery quantum rules directly to smooth spacetime, the calculations break down. The equations spit out infinities and unsolvable errors. This mathematical breakdown proves that our current models are fundamentally incomplete. They describe two different realities that share no common language. Proving exactly how these two theories might reconcile is hindered by a massive physical barrier, the Planck scale. This is the domain where quantum gravitational effects actually matter. It sits at roughly 10 to the power of -35 meters. To probe something that infinitesimally small requires an unimaginably dense concentration of energy. This machine represents the limit of current technology, yet its collision energies fall short of the Planck scale by roughly 15 orders of magnitude. Because the testing ground for quantum gravity is so far beyond our physical reach, any proposed solution to merge these frameworks is currently trapped in the realm of indirect observation and pure theory. The drive to unify the laws of nature is physics' oldest tradition. It took shape when Isaac Newton proved that the same force causing an apple to fall also governed the orbits of the planets.
3 centuries later, Albert Einstein spent the final 30 years of his life in near isolation, trying to construct a classical unified field theory to merge gravity and electromagnetism. His efforts stalled for 2 specific reasons. First, he refused to accept quantum probability as a true reflection of reality. Second, the strong and weak nuclear forces were not yet fully mapped out by science. While Einstein worked alone, the rest of the physics community pushed forward. By the late 20th century, they successfully unified electromagnetism with the weak and strong nuclear forces from the bottom up, creating the Standard Model. The Standard Model is the most rigorously tested scientific framework in human history.
Yet it entirely excludes gravity, which means our picture of reality is still fractured at its base. To fix this broken machine, late 20th century physicists developed string theory, which later evolved into M-theory. Instead of treating subatomic elements as zero-dimensional dots, string theory proposes they are tiny, one-dimensional vibrating strings. Depending on how a string vibrates, it produces different particles, and crucially, one of those vibrations naturally produces the graviton, a hypothetical particle for gravity. But this structural solution comes with a heavy mathematical cost. For the equations to work, the theory requires the existence of supersymmetry, along with 10 or 11 dimensions of spacetime. Because these extra dimensions can fold up in astronomical numbers of ways, the theory predicts roughly 10 to the power of 500 possible universes. This landscape problem makes it nearly impossible to extract unique, testable predictions about our specific universe. Rival frameworks attempt to avoid these extra dimensions altogether. Loop quantum gravity, for instance, focuses strictly on spacetime, attempting to quantize it into a microscopic, discrete web of spin networks. Despite the immense mathematical elegance of these structural approaches, none have produced direct experimental confirmation. By treating unification purely as a structural problem, we have traded a direct mathematical contradiction for infinite, untestable complexity. The physics community has essentially reached a dead end. What if the failure to unite these models isn't a problem of missing math, but a result of ignoring a core component of reality itself? There is a historical precedent for this shift. Physicist John Archibald Wheeler proposed the it from bit concept, arguing that the universe is built fundamentally on information, placing the observer firmly at the center of physical processes. This connects directly to the long-standing quantum measurement problem. It suggests the act of observation serves as the active mechanism bridging the probabilistic quantum realm with concrete classical reality. This epistemological shift is the basis of a modern research program formalized around 2026, known as ODTOE, or Observer-Dependent Theory of Everything. Instead of building extra dimensions, ODTOE treats the observer as a fundamental primitive. It posits that reality is not a pre-existing stage, but a specific configuration actualized solely by the act of observation. The goal of this framework is to derive the fundamental constants of nature directly from the geometry of self-observation, attempting to calculate known values without relying on unexplained variables.
While ODTOE is a theoretical program still developing its empirical tests, it represents a strict re-evaluation of the rules. If the structural math is exhausted, the observer's place in physics requires serious scrutiny. Whether the answer lies in strings, in quantized geometry, or observer dynamics, the final master equation remains out of our grasp. Our inability to find this final mathematical link means the mechanics of the universe are vastly deeper and more intricate than early 20th century physicists anticipated. The absence of a theory everything is not a failure of science. The search itself continues to act as the most powerful catalyst for expanding human knowledge, reminding us that physics is an ongoing quest to understand the foundation of where we are.